Hello everyone. Today we are going to do an important topic of your IB papers and other boards, which is called as VSEPR theory, present in chemical bonding. It's a part of chemical bonding topic, which is in IB it is structure 2.2. Okay. What is VSEPR? The V in the VSEPR theory stands for valence. Then S stands for shell, valence shell. E stands for electron, valence shell electron. And the P stands for the pair, and this R stands for repulsion. Valence shell electron pair repulsion theory is the name of this VSEPR theory. Okay, what this theory based on and what it helps us? This theory helps us to find the shape and geometry of molecules. By the help of this theory, we can find out the shape and geometry of molecules. Shape and geometry of molecules. On what basis? On the basis of number of electron pairs the molecule has. Electron pairs or electron clouds, we can say. You can see in this document, the VSEPR theory, which is valence electron pair repulsion theory, is given by Sidgwick and Powell. These are the two scientists who put forward the idea of this theory. And then some other two scientists, they also developed this theory further. And this present document is based on Sidgwick and Powell's theory, which says that this theory, which is called as VSEPR theory, it helps in identifying or finding the shapes of covalent molecules on the basis of their repulsive interaction between the electron clouds or the valence electron. And these valence electron could be of two types, lone pair and bond pairs. Thus, the electron clouds present in a molecule will control the shape and geometry of the molecule. Now, the shape and geometry of molecule basically depends on the electron clouds of the central atom. Now, what will be the central atom? Central atom will be the least electronegative element of the molecule. If I talk about, suppose NH4 plus nitrogen will be my central atom, not hydrogen. Why? Because although hydrogen is least electronegative, it cannot form more than one bonds. Hence, nitrogen will be my central atom. But if I talk about PCl3, phosphorus is less electronegative than chlorine, therefore phosphorus will be the central atom. Got it? Hydrogen cannot be a central atom. Rest in all you can find out by the help of least electronegative element, which is a central atom. Now, a central atom always has two types of electron clouds, bond pairs and lone pairs can also be present. Always have bond pairs, but there can be non-bonding electron clouds, which are lone pairs also. They can also be present in a molecule. The shape of molecule depends on the number and nature of the electron pairs present in the valence shell of central atom. Number, how many electron clouds are present in nature, whether they are lone pairs or bond pairs, as they have repulsive interaction between each other. Now, what are the important postulates of this topic? This VSEPR theory, if a molecule has only two atoms with two electron clouds and both are bond pairs, then the shape of the molecule will be always linear. What I mean is, if a central atom, suppose beryllium bonded to hydrogen and then bonded to hydrogen, there are two electron clouds. The shape and geometry will be linear and the bond angle will be 180 degree, which we'll talk later. What this theory says, the shape and geometry of a molecule with two atoms, two bonded atoms will always be linear. As you can see in this video, the shape and geometry of the molecule will be linear. Thus, according to the VSEPR theory given by the Sidgwick and Powell, the shape and geometry of a molecule containing two electron clouds and which both are bond pairs will be always linear. That is, if a central atom is bonded to two atoms, it has two electron clouds, and the shape and geometry of such molecule will be always linear. The second point is, if a molecule has three or more than three atoms, and one of the atoms is called a central atom, which we already know. Central atom is linked to similar atoms and surrounded by bond pairs, then the repulsive interaction between them will be similar, and the shape of molecule will be symmetrical and geometry is regular. That is, if the central atom is bonded to same type of atoms and these are only bond pair electrons present in the central atom, then the shape and geometry of molecule will be regular. Shape is symmetrical and geometry will be regular. Now, but if the central atom is linked to different atoms and is surrounded by, or if surrounded by bond pairs and lone pairs, different atoms, or if surrounded by bond pairs and lone pairs, now there will be repulsive interaction between these lone pairs, and the extent of repulsive interaction will be different. Due to the difference in the repulsive interaction, the shape and geometry of molecule become unsymmetrical and distorted. Okay, if there are two electron clouds, always linear, but when there are three or more than three, and out of these three, if all of them are bond pairs, then the regular geometry. But if some are bond pairs and lone pairs, then the geometry gets distorted. Now, the order of repulsion or the distortion between the electron clouds depends on the repulsive interaction of the electron clouds. The most or the strongest repulsion is between lone pair, then lone pair, bond pair, and the least between bond pair and bond pairs. Since the lone pair, they have maximum repulsive interaction, therefore they try to arrange themselves at the farthest distance from each other. So when the shape and geometry of molecule, due to the repulsive interaction of lone pair, is formed, the molecule tries to attain or tries to arrange the lone pairs at the farthest distance from each other. Okay, the exact shape of molecule depends on the total number of electron pairs present around the central atom. What it means, if the molecule has 3 electron pairs, then its shape will be trigonal planar. We'll do in the table down, planar. If it has 4, then it is tetrahedral, and so on. Okay, so the point says the exact shape and geometry of molecule depends on the number of electron clouds a molecule has. And in order to minimize the repulsion and maximize the stabilities, the electron pair tries to arrange farthest distance away from each other. And since the lone pairs are under the influence of one nucleus, they have maximum repulsion. Thus, they occupy the most or more space, that is, they are at the farthest distance. The molecule tries to keep the lone pairs at the farthest distance. Okay, these are the important postulates of this VSEPR theory. Two atoms, recall again quickly, two atoms, bond pairs, and both are bond pairs, shape will be linear. More than two atoms and all three, that more than two, that is three or more, and all of them they are bond pairs, shape will be regular and symmetrical. Geometry will be regular and the shape will be symmetrical. If the molecule has both lone pairs and bond pairs, then due to repulsive interaction between lone pair and bond pairs, the shape and geometry of molecule becomes distorted and unsymmetrical. And the extent of distortion depends on the repulsive interaction between the electron clouds. Maximum repulsive interaction is between lone pair, then lone pair, and bond pair. The shape and geometry or the exact shape and geometry molecule depends on total number of electron pairs present around the central atom. If the total number of electron pairs, they're all bond pairs, and if suppose there are 3 bond pairs, the shape regular geometry will be trigonal planar. 4, tetrahedral. 5, it is trigonal bipyramidal, and so on, which we have tabulated in a table coming in the down. In order to minimize the repulsion and maximize the stability, the molecule tries to arrange its electron clouds at the farthest distance from each other. And since lone pairs, they have maximum repulsion because they are under the influence of one nuclei. They are present on one nuclei of the molecule, whereas bond pairs are present on the 2 nuclei. Thus, lone pairs, they will have more repulsion and they have to be placed at the farthest distance from each other. Therefore, they occupy the more space. So these are the important postulates of VSEPR theory. They can ask you give some postulates or write the postulates of VSEPR theory. There was a question in IB in past papers where some postulates of VSEPR theory were asked. Now we'll talk about the shape and geometry of molecules, various molecules on the basis of electron clouds, lone pair, bond pairs, and what are the actual shape and the distorted shape on the basis of electron clouds in the coming topic. Now if you see this table on the basis of VSEPR theory, we had tried to tabulate the shape and geometry of molecules on the basis of number of electron clouds the molecule has and number of bond pairs or lone pairs the molecule has. To start with, if a molecule has 2 electron clouds, these are electron clouds or charge clouds, we also call them charge clouds, and all of them they are bond pairs. Number of bond mean bond pairs. All of them bond pairs, there's no lone pair. The shape and geometry at which these bond pairs can be arranged at the maximum distance is linear. Example is carbon dioxide and beryllium hydride. BeCl2 also has shape and geometry linear because it has 2 electron clouds. Now if a molecule has 3 electron clouds and out of these 3, all the 3 they are bond pairs, no lone pair, then the shape and geometry of molecule will be regular. And the regular shape and geometry with all 3 bond pairs is trigonal planar. And for trigonal planar structure, the most common example is boron trifluoride BF3, in which the 3 BF bonds, they are arranged at an angle of 120 degree with each other, giving a shape trigonal planar shape to the molecule. The bond angles between all these is 120 degree. The shape and geometry of 3 electron clouds with all 3 bond pairs, no lone pair, is trigonal planar and the bond angles are 120 degree. Example is boron trifluoride. Now if instead of all bond pairs, if the molecule has two bond pairs and one lone pair, out of the three electron clouds, two are my bond pairs and one is lone pair, and two are bond pairs and one lone pair, and this has converted to a lone pair. Due to repulsion between these bond pairs and lone pairs, the shape and geometry changes to band shape. From trigonal, planar, regular geometry, the shape changes to band shape. The example is SO2. The other example is ozone, O3, in which the two ozone atoms, that is two oxygen atoms of the ozone, the two OO bonds of the ozone, they are having a band shape, and the bond angle will be less than 120 degree. We can write less than 120 degree, but in case of ozone, we know it is 117 degree, so you can write 117 degree. The shape and geometry will change. So whenever it's a distorted shape, you can always write less than the regular geometry bond angles. The bond angles you can write less than 120. If I don't know, suppose I don't know the bond angles of SO2, I can write, if they ask you, less than 120 degree. Regular geometry bond angle you can write, since the regular geometry has 120 degree bond angle, this distorted structure of the molecule with three electron clouds will have less than 120 degree bond angle. Because of repulsion, these two bonds come closer to each other and the bond angle will decrease. Okay, for three electron clouds, regular geometry is trigonal planar, and with three electron clouds and out of three, two bond pairs, one lone pair, it is band shape or angular shape. We can also say angular shape or V shape. All are same. Now the next is when the molecule has four electron clouds, and out of these four, all the four are bond pairs, no lone pairs. Then the shape and geometry of the molecule will be regular, symmetrical shape, regular geometry, and the regular geometry is tetrahedral. As you can see in methane, all the four bonds they are at an angle of 109.5 degree with each other. For the regular geometry tetrahedral, the bond angle will be 109.5 degree. The four bonds are at the four corners of a tetrahedron, and the bond angles are 109.5 degree. Thus 4 plus 0 is 109.5 regular geometry. But when out of these four, three electron clouds are bond pairs and one converted to lone pair. Three bond pairs, one lone pair. Now one of this has converted to lone pair, so this is suppose my lone pair, and these three are bond pairs. The shape changes to trigonal pyramidal. Due to repulsion, these bonds will come closer. Lone pair will repel these bond pairs and the bond will come closer. Therefore, the bond angles will decrease from 109.5. So I can say, if they ask you what is the bond angle of a molecule having three bond pairs and one lone pair, then the bond angle will be less than 109.5 if I don't know it. But since ammonia is in my course, I should remember the bond angles of ammonia. It is 107 degree. Ammonia is an example of trigonal pyramidal shape with three bond pairs and one lone pair. Now the next condition for the four electron clouds will be 2 plus 2. Two bond pairs and two lone pairs, that can be the next condition when the four electron clouds are there. Now these two electron clouds, these two will convert into my lone pairs, so these two are my lone pairs. And these are bond pairs. The lone pair repel the bond pairs more, they will come more closer, and the shape changes to band or angular shape. We call it band or angular, and the bond angles again will be less than 109.5. Whenever we write about the bond angles of the distorted molecule, we have to write only in terms of regular geometry, which is 109.5. What I will write in terms of this regular geometry, less than 109.5. But since water is in our course, therefore the bond angle of water, which is 104.5 degree, I should remember. The example of 2 plus 2 is water. So 4 electron clouds, 4 plus 0, 3 plus 1 and 2 plus 2. 4 plus 0, which is regular geometry. Regular geometry is my tetrahedral. Bond angles are 109.5. Example is methane. When it is 3 plus 1, then it is trigonal pyramidal, one lone pair repels, the bond angle decreases from 109.5. 2 plus 2, two bond pairs, two lone pairs, bond angle further decreases and it is less than 109.5. Shape is angular, band shape or V shape. Okay, we need not to remember these examples. In the coming video, I am going to share you a shortcut method for finding out without learning the examples what is the shape and geometry. Simply we'll make a table of electron clouds and then I can identify how many number of electron clouds are there, and by the help of that I can predict the shape and geometry of any molecule. We do in the next video, we'll see it. Now the next is 5 electron clouds. If a molecule has 5 electron clouds, condition number 1, 5 plus 0, all the 5 they are bond pairs and there is no lone pair. And it is the regular geometry, and the regular geometry is called as trigonal bipyramidal. The 3 bond angles which are called as the equatorial, these are my equatorial bond angles, equatorial. These 3 bond angles, equatorial bond angles, they are at an angle of 120 degree. These 3 are at an angle of 120 degree with each other. These are called as equatorial bonds. Whereas the remaining these two are my axial bonds. We call them axial bonds. They are present 90 degree to the plane containing these equatorial bonds and the bond angles are 90 degree. So thus there are two types of bond angles, 120 degree and 90 degree in PCl5 or a molecule having a trigonal bipyramidal geometry. Trigonal, this is my trigonal geometry, and one above the plane and one below the plane, bipyramidal. Now in PCl5, one more question comes. PCl5, these three bonds, they are shorter, and these two bonds, which are my axial bond, they are longer. These are longer bonds. Why? Because the two axial bonds, they are repelled by three electron clouds of the equatorial bonds. These two axial bonds, these two, they are repelled by the three electron clouds of the equatorial bonds. Hence, they will move away from the central atom and thus become longer. Thus, they can ask you, why does PCl5 easily dissociate to form PCl3 and Cl2? The reason is the two equatorial bonds, the two axial bonds, they are weaker and they will easily dissociate and convert into chlorine. Remaining molecule will be PCl3. Got it? Now, what's the shape and geometry of PCl3? That we can find out by the help of a shortcut method, which I will explain you in the further video. Got it? So, what we should remember in this PCl5, the axial bonds and the equatorial bonds, these are my axial bonds. And these are my equatorial bonds. So two are axial and two are equatorial bonds, which we should remember. So these are three equatorial bonds which are at an angle of 120 degree. These are equatorial bonds, and these two, they are my axial bonds, which are one above the plane and one below the plane. The bond angle with the plane is 90 degree, and bond angle between these two axial bonds is 180 degree. With the plane 90 degree, between the two axial bonds is 180 degree. Now since these bonds or the bond length of axial bond, they are longer, therefore they are weaker bonds. Hence PCl5 on heating easily dissociate to form PCl3 and Cl2. Okay. Now the next is 4 bond pairs, 1 lone pair. Out of the 5 electron clouds, 4 are bond pairs and 1 is lone pair. Now one of this is converted to lone pair. The lone pair will be at 120 degree. Why? Because 120 degree is the maximum angle at which the lone pair could be present to minimize the repulsion. Thus 120 degree, that is the equatorial position, will become lone pair, and the remaining 2 will be my bond pairs at equatorial. 2 equatorial and 2 axials. The shape is called as seesaw, also called as sawhorse. Sawhorse, we also call it sawhorse. And what are the bond angles? You have to write less than 120 degree and less than 90 degree. Example is SF4. For 4 bond pairs and 1 lone pairs, the shape is sawhorse or seesaw. Bond angles are less than 120 degree because of the repulsion. These bond angles, these bonds come closer, and thus the bond angle will decrease from 120 degree and 90 degree. Example is SF4. Next condition is when out of the 5 electron clouds, 3 are my bond pairs and 2 are lone pairs. 5 electron clouds, 3 bond pairs and 2 lone pairs. The lone pairs must be at maximum distance from each other, that will be 120 degree, so that they have minimum repulsion. And due to this repulsion, the bond angles will remain 90 degree. From 120 degree, all the bond angles converted to 90 degree. Only the lone pairs will be at 120 degree with each other, but the bond pairs will be at 90 degree. Therefore, the shape of the molecule will be T-shape. Example, in ClF3, the 2 ClF bonds, they will be at 90 degree with each other, and the shape is a T-shape. Now, 3 electron clouds are lone pairs and 2 electron clouds are bond pairs. It's 2 plus 3. Out of the 5, 3 electron clouds are lone pairs and 2 are bond pairs. That is 2 bond pairs and 3 lone pairs, we can say. Now, the 3 lone pairs will be at 120 degree with each other, and the 2 bond pairs will be at the linear position, and the shape is called as linear. Example is I3 minus, which is the best example of this. Bond angles are 90 degree. The bond angle between these two will be 90 degree bond angles. Okay. Now the next is 6 electron clouds. When a molecule has 6 electron clouds, and out of that 6 plus 0, that is all the 6, they are bond pairs. 0 lone pair. Shape is again regular. We call it the regular shape, and the regular shape is called as octahedral. Octahedral will be the regular shape of this molecule, also called as square bipyramidal. Square bipyramidal, octahedral, when the same thing. All the bonds, all the bond pairs, they are at angle of 90 degree with each other. Hence the shape will be square bipyramidal, bond angle 90 degree. Example SF6. But if out of this 6 electron cloud, 5 are lone pairs, 5 are bond pairs. Now next is, out of the 6 electron clouds, 5 are bond pairs and 1 lone pair. 1 lone pair here, the shape changes to square pyramidal, and since the lone pair and bond pair, they are equal distance, the bond angle still remains 90 degree. Example, ClF5 can be the example of this compound, or SbCl5 can be an example. SbCl5 2 minus can be an example of this. Next is, out of the 6 electron clouds, 4 are bond pairs and 2 are lone pairs. Now these two becomes lone pairs, the shape changes to square planar and the bond angles are again 90 degree. Example XCF4. XCF4 is the best example of this. Square planar geometry, 90 degree bond angles. Thus, that's all about this table. So by this table, we can find out the shape and geometry of molecules based on the number of electron clouds and then classification of electron cloud, lone pairs and bond pairs. Now, all these examples you need not to remember. Only thing you have to remember is how many electron clouds, how many lone pair and bond pairs, and what is the regular geometry and distorted geometry. Name of the distorted and regular geometry. Rest all we can find out by the help of a shortcut method coming in the next video. Okay, this I tried to explain you the VSEPR theory on the basis of the structures and diagrams of the molecules, the electron clouds. On the basis of electron clouds, the molecule forms. Okay, to summarize it, we can say if a molecule has only bond pairs, which is a regular geometry. If a molecule has bond pair means it has a regular geometry. And for regular geometry with 2 electron clouds, linear. 3 electron clouds, trigonal planar. 4, tetrahedral. 5, trigonal bipyramidal. 6, octahedral. And 7, pentagonal bipyramidal. 7 is although not in the course of IB. And only one example of this is IF7. If you want, you can remember it. Okay. Now, shape of molecules with bond pairs and lone pairs both. This was on the basis of bond pairs only, which is a regular geometry. Now, if a molecule has bond pair and lone pair both, I call it distorted geometry. And for this, if the bond pairs are 2 and 1 lone pair, that is total number of electron cloud 3. The electron cloud structure will be trigonal planar. This is the important thing. Electron cloud structure, we should always remember difference between electron cloud structure and actual structure. Actual structure depends on the bond pairs repelled by lone pairs, whereas the electron cloud structure depends on the total number of bond pairs and lone pairs. What I mean to say, if a molecule has 3 electron clouds, then the regular geometry is trigonal planar as per this, and the electron cloud geometry is also trigonal planar, which is my regular geometry. We can say electron cloud geometry represents the regular geometry, whereas actual structure depends on the repulsive interaction between lone pair and bond pairs, and thus the shape changes. Thus, for this 2 bond pairs and 1 lone pair having 3 electron cloud, the electron cloud geometry will be trigonal planar, but the actual geometry is angular band shape. Example SO2, SnCl2, etc. Now, if a molecule has 4 electron clouds and out of 4, 3 plus 1, 3 bond pairs, 1 lone pair, electron cloud geometry, tetrahedral for both 4, but for 3 plus 1 it is trigonal pyramidal, and for 2 plus 2 it is angular. Same way for 5 electron clouds, condition number 1 is 4 plus 1, 3 plus 2 and 2 plus 2. All of them have a electron cloud geometry trigonal bipyramidal because all of them have 5 electron clouds. But 4 plus 1 will have a seesaw sword shape, 3 plus 2 will have a T shape, and 2 plus 3 will have a linear shape. Okay. Now, if a molecule has 6 electron clouds, the shape is octahedral regular shape, electron cloud geometry. But the condition number is 5 plus 1, square pyramidal. 4 plus 2, square planar. So these tables you have to learn, you have to remember. And by knowing these tables, you can simply identify the shape and geometry of molecules if you go through the video which I am going to share about the shortcut methods of finding structure and shape of molecules from VSEPR theory. Okay, I hope this will be helpful to you. Thank you very much.